Have you ever wondered why the Earth seems to be locked into an orbit around the Sun? Why do smaller bodies like the Moon revolve around larger bodies like the Earth? Why doesn't the Earth crash into the Sun? What forces are at play in these phenomena? Here, we will delve into those mysteries that intrigued physicists for centuries. Welcome to Gravitation and Orbits. Newton's universal law of gravitation was a groundbreaking development that brought together gravity and astronomical phenomena. It states that every mass attracts every other mass with a force acting along an imaginary line connecting them. This attractive force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Mathematically, this is expressed as capital F is equal to capital G times capital M times lowercase m divided by r squared. Here, F represents the attractive force. G is the gravitational constant, 6.67 times 10 to the negative 11th. Capital M and lowercase m are the two masses where capital M often denotes the larger mass. And r is the distance between their centers of mass. In addition, the force between the objects is a Newton's third law pair, and they are equal and opposite. It's crucial to note that Newton's law of gravitation applies to point masses. However, in cases where stars and planets have considerable distances between them, we can treat them as point masses and apply the law. In addition, stars and planets are spherical bodies with relatively uniform mass distribution, and thus their gravitational effects can be approximated using the center of mass as a point mass. When using Newton's law of gravitation, we must ensure that the masses are in kilograms and the distance is in meters. This makes them SI units, and they match the units in the gravitational constant. Newton's law of gravitation is a classic example of the inverse square law, a principle which applies not only to gravity but also to sound, light, and various physics phenomena. If we examine the graph and the equation of this relationship, we can see that the force is proportional to the inverse square of the distance between objects. In simple terms, it implies that as masses move farther apart, the gravitational force decreases rapidly, never quite reaching zero. This concept is intuitive. The greater the distance between two celestial bodies, the weaker their gravitational attraction. Gravitational field strength is defined as the force per unit mass acting on a small test mass in a gravitational field. That means that if I place a small test mass, let's say right here, it will experience a gravitational force proportional to its mass. The test mass itself is defined as so small that it doesn't affect the field it is placed in. As shown in the picture, gravitational fields can be represented by field lines that show the direction that the gravitational force would act on a mass placed at different locations. The field line density shows the strength of the field. Where the lines are closer together, the field is stronger, and where they are farther apart, the gravitational field is weaker. Like a gravitational force, the gravitational field decreases at the square of the distance from the mass. Thus, another inverse square relationship. To explore the relationship between gravitational force and gravitational field strength, let's use the International Space Station, the ISS, as an example. From Newton's law of gravitation, we see that F is equal to G times M divided by r squared. We will call capital M the mass of the Earth, and lowercase m the mass of the ISS. R is the distance between their centers of mass. F is the gravitational force between those two masses, or according to Newton's third law, the force of the Earth on the ISS, as well as the force of the ISS on Earth. We also have the equation G is equal to F divided by m, where G is the gravitational field strength, F is the force in newtons, and m is the mass of the object in the gravitational field. Note that the units for gravitational field strength are newtons per kilogram. If we put this in terms of the ISS, it becomes the gravitational field strength is equal to the gravitational force between the ISS and Earth divided by the mass of the ISS. Substituting Newton's law of gravitation for the force, we get lowercase g is equal to capital G times mass of the Earth times the mass of the ISS divided by r squared, and all of this is divided by the mass of the ISS. The mass of the ISS cancels out, and we see that the gravitational field is equal to capital G times the mass of the Earth divided by the distance squared. Notice that the mass in this equation is the mass of the body causing the gravitational field at that point in space, in this case, Earth. The general form of this equation is here. Gravitational field strength is equal to the gravitational constant times the mass causing the gravitational field divided by the square of the distance to the mass. This equation allows us to determine the gravitational field at any location. Notice that the gravitational field strength at a specific point is independent of what mass is located at that point. You may recognize G from your use of G is equal to 9.8 newtons per kilogram. Note that the value of 9.8 happens to be the answer you get if you use the formula G is equal to G times m divided by r squared and substitute in the mass and radius of the Earth. This gives 9.8 newtons per kilogram as the gravitational field strength at the surface of the Earth, which also corresponds to the acceleration of freefall at the Earth's surface, where newtons per kilogram and meters per second squared are equivalent units. Many struggle to distinguish between gravitational fields and gravitational forces. To help overcome this difficult concept, think about the ISS in this situation. Regardless if the ISS is there or not, Earth is there, causing a gravitational field at that point. The strength of that gravitational field can even be calculated using our equation. However, there is no force there. Once I place the ISS in that gravitational field, now there is a force of gravity on the ISS from Earth, and a force of gravity on the Earth from the ISS, as illustrated by our equations. Therefore, a gravitational field is always there. However, a gravitational force is only applied when objects with mass are placed in the gravitational field. Now that we have a clearer understanding of the distinction between gravitational fields and gravitational forces, we must ask, why doesn't the ISS or objects like the moon crash into Earth? Why doesn't the Earth crash into the sun? The answer is orbital velocity. Even though there is a gravitational pull towards Earth, orbiting objects such as the ISS or the moon have a high enough tangential velocity that they do not crash into Earth. When an object is in orbit, gravity provides the centripetal force. The centripetal force equation is F equals m times v squared over r, where F in this case is the gravitational force from Earth, m is the mass of the object in centripetal motion, v is the object's velocity, and r again is the distance to the center of mass of the object providing the force, in this case, the center of the Earth. Equating this equation to Newton's law of gravitation, we see that the smaller masses cancel out. An r also cancels out, removing the square. We can then solve for the velocity of the object in orbit. V is equal to the square root of capital G times the mass of the object causing the gravitational field, again in our case Earth, divided by the radius. This formula shows the speed that a satellite would need to maintain a circular orbit of radius r around a planet or star of mass m. Note that for any given radius, there is only one velocity that will result in a circular orbit, and that velocity needed to orbit decreases as the radius increases. Today, we took a journey through the intricate realm of gravitation and orbits. From unraveling the universal law of gravitation, the gravitational force that governs celestial bodies, to exploring the concept of gravitational fields that extend their influence through space, we've gained insight into the forces shaping the cosmos. We've explored the mechanics behind gravity and the captivating movement of celestial bodies in our vast universe. Thanks for watching.